Your time now.
Okay, so first of all, thank you very much for showing up and listening to my presentation. A few words about myself. That's me with my wonderful family. I'm father of 3 girls, but at least my dog is a male. I'm a software engineer from Torino, Italy. It's northwest of Italy. And I always worked as a consultant. I founded my first company when I was 18 and I started the university to pay the bills. I'm passionate about free software. I'm an official Debian developer and Ubuntu developer since 2004, mainly related to Python packaging. And I work as a software engineer and system integrator at Evosip. I love sailing, as you can see. I love snowboarding. As a system integrator, I like to combine the two, so I will try kite surfing this summer. A few words about Evosip. We were here last year to present our platform. There is a video on YouTube about the presentation of our software. We build a voice over IP platform as a service. We use Docker. And we started orchestrating our infrastructure on Kubernetes to build a scalable, self-healing, multi-tenant, and geographically distributed platform. As I said, I'm mainly a software engineer and developer. I'm not a SIP engineer. So I spent a lot of time in these 3 days here at the Kamailio World asking people about their building systems, how they solve the building, because it looks like building is a big issue for you. And I have the impression that we have different meanings for what a building platform is. Usually we talk about traditional building where we start from the CDR and we build up the invoicing, accounting, and the integration with our CRMs. What we develop for our platform is a real-time building deeply integrated in Kamailio. What does it mean? It means that we call the billing system each time we have to authorize a call, asking if a given account can call a given destination, and for how long. So what is the maximum length of the call, which is a load. And we do LCR in the same time. We do signaling when we start a call, when we end the call, and we deeply integrate in the flow of the call. So we can, for example, terminate the call when anomaly is detected or when the anti-fraud triggers. So let's summarize what we wanted from our building system. The first 2 are quite obvious. As we deploy on Kubernetes, we wanted a system that is cloud native, Kubernetes-based, so we can deploy it in the same infrastructure we use for our own software. We designed it to be domain agnostic, so not just for voice, but also for messages, for data, or for IoT. We want it to be real-time to provide additional features that we can provide to our users and our customers, and the blockchain enabled, but we will discover it later during the presentation. Let's have a look at the main topics that I will go through during the presentation. We will talk about performance and scalability, the availability of the platform, the integration with data in real time, and last but not least, the blockchain. So let's start from the first one, performance and scalability. When we designed our platform, we started with a brainstorming, and the first bullet point we wrote on the paper was we want our billing platform to be API-based. We want to hide all the complexity to the caller, and we want to expose a simple-to-use API, HTTP-based if it's possible. We use services inside Kubernetes. How many of you are running Kubernetes in production? Can you raise your hand? OK, just a few. A service is a load balancer. It's a load balancer you get for free inside Kubernetes, and it will load balance your requests among all the instances of your software, which are called pods in Kubernetes. So Kamailio is using JSON RPC calls, HTTP-based, to ask to the building service the answers it needs to perform the authorization, the start of the call, and the end of the call. And Kubernetes is load balancing across all the instances that we run inside the system. So looks pretty easy. Let's go deeper, and let's check out how the integration works. This is an example of Kamailio code for the authorization request. So Pretty simple for you, a bit harder for me, as I'm not a Kamailio expert, but we are building a JSON document, setting variables needed to the building to perform an authorization. In this case, we included source and destination, but we have several other variables that we pass to the building. Then we make an HTTP call to a specific endpoint, which is the one where the building is waiting for and provided by Kubernetes, using the HTTP async query and asking the answer to be managed by the root. This way, the Kamailio worker is not blocking anymore because it's suspending the transaction, and it's free to do something else. This is because the authorization is quite costly. It takes several tens of milliseconds to perform authorization, LCR, and calculate the balance, so the maximum length of the call for the account and all the tiers up, the partner, the tenant, and so on. We manage the response in a specific route. Again, pretty simple. We check if the answer is 200, so everything is OK. We extract from the JSON, from the response, the variables we need. And in case the authorization fails, we route to a different specific route inside the Kamailio code. For example, no channels are available anymore, or the balance is not enough, or the destination is not enabled as a price list for that specific account. Again, pretty simple. In this code, this is just an example. We don't manage errors. We don't manage a lot of things. But just to give you an idea about it works. Pretty much the same when the call starts. So again, we build a JSON. We set the variables, for example, the transaction ID, which is the call ID. We make the call, and we handle the response. Again, we don't handle errors in this sample code. We just log, OK, successful, or we send back a 500 billing was not available. Same pattern for call end, so you get the idea. But what is happening behind the curtains? As you see, it's pretty simple. We have an HTTP server waiting for somebody to make a call. It's synchronous from the caller point of view. Let's skip the fact that we're using the HTTP async library. What is happening behind it? So let's dig deeper into the building. How can we manage a building system which offers an API interface that can scale to hundreds, thousands of calls per second in a critical integration? Because if the building is not available, then we can't make a call. The answer is pretty simple. We use the same technology we use for web applications. So we built an ecosystem of micro components. A microsystem of independent components that talk each other. Why microservices? Because they are easy to manage, easy to test, easy to deploy. We can scale up and down single components based on the bottlenecks. We don't have to scale up the whole building platform. We just have several components that are independent. And I want to underline the startup time matters, because especially with Kubernetes, you describe your deployment and you let Kubernetes manage it, which means that pods are ephemeral. You can have a pod shutting down and being relocated on a different worker. And your instance, your component should be very fast to be up and running, ready to answer to requests. But how do we manage these components? We run Docker containers, and we use Kubernetes for the orchestration. You say everything looks easy. You have stateless components. But what about the data? Where do you store the data? Here we have a religion war, more or less, because somebody says, you can run your own database inside Kubernetes. We tried. We failed. We believe that databases are not the perfect use case for Kubernetes. You can do that if you know exactly what you are doing. We run our databases outside Kubernetes because you can't really scale up as you want. We selected different databases, different solutions. We use both SQL-based, Postgres, and NoSQL-based MongoDB databases for different scenarios inside the building platform, and they are outside the Kubernetes and exposed as a services. Here you have a simple diagram about Kubernetes running several nodes, each one with pods. But how do we move data inside this ecosystem of microcomponents? This is a diagram of our system where a few of the microcomponents are drawn. We use a message bus. So all the components are linked to a message bus, and we use the message bus to carry not only messages for the communication between the components, but also requests, the data you need to answer, and the responses. So for us, the message bus is like a highway, and we do all the data transportation we need on that highway. There is a single access point to data, which is the special component we call API. The API is responsible for data retrieval and data storage, so read and write. It's called by the other components. Then all the communication happens through the message bus. The agent, the one that we call from Kamailio, has no direct access to the database. It's just placing messages on the message bus and waiting the answer on the same message bus. But things get even more interesting when you think about different data centers, because we designed our platform to be without any single point of failure. So we run different data centers of different worker nodes of Kamailio, each one with different instances, multiple instances of our components, and we share the message bus across all the worker nodes. The components are disposable. We can kill them, and they will get restarted, and no message is lost because the message bus is handling it for us. Same stuff about geographical distribution. It's the same if you run different nodes in the same data center or in multiple data centers. You can use different policies to get the data and the service as near as possible to the user. But you can say, everything is just wonderful, but I'm small. I don't need to replicate my data in different data centers. This is just too much for me. The truth is that this is what you can do with Kubernetes, but this is not only what you want to do with Kubernetes. Kubernetes offers you a very important feature out of the box, even if you start it on free nodes in your own data center, which is horizontal, predictable, linear scalability. It means that if you design your software to be run in Kubernetes, you can scale it using the API of Kubernetes in a linear way. So you can manage 10 calls per second, 100, 1,000, 10,000 calls per second, and grow linearly using multiple instances of the same software. The final goal, when we designed the billing platform, was to have a system which is self-healing. We wanted to be ready to lose one worker node of Kubernetes without affecting our customers, without losing calls. And this is possible because the platform we have underneath Kubernetes offers this out of the box. They are doing it since 2013, 2014 in the web world. We are doing the same in the telco world, but it works this way. We are using readiness liveness probes. If something gets wrong and one of the pods is not responding anymore, Kubernetes will just kill it and relocate it to another worker node. And everything will continue to work. We are using the same tools that are used in the Kubernetes world outside the telco world. So monitoring, logging, is everything out of the box. But now let's talk about data integrity and real time, which will bring us to the blockchain. Well, we think that real time means really real time. I had a couple of chats with somebody who told me that the real-time billing system was injecting CDRs every 20 minutes. That's not real time. We are doing real time with a per second precision. We are checking the balance and analyzing the data every single second. This means that our database should be always consistent. We use, as I've told you, different SQL database and NoSQL database. And we are using asynchronous data consolidation to be able to perform real-time checks. It means that we don't write to the database when it is not needed. We use a write-ahead logic. If you know Postgres, for example, it's quite a common word. And we take into account the transaction logs when we are processing the billing data before doing consolidation to the database. We try to delay the consolidation, because it can be done later. It doesn't affect the calculation of the building. The asynchronous data consolidation gives us interesting plug points for event-based processing and allows us to have additional high-level features that are linked to events that happen inside the building. The data retrieval and storage, as explained before, happens through an API, which has a specialized cache, as it is the single source for data retrieval and storage. We are quite aggressive with cache. And this is exactly where the event-based system works. We have webhook and callback to let us inform if something happens, if an account is blocked, because the anti-fraud trigger. More interestingly, we use the real-time data to do data processing. What you see in the screenshot is a time series based on the Prophet Python library from Facebook. And we use these kind of tools for doing anomaly detection. The black points on the graph are outliers, so data that are outside the typical time series for that specific account or that specific tenant. This is the way we do anti-fraud, using both statically defined rules as well as simple machine learning tools to analyze the past behavior of the accounts and comparing it to what is happening in that specific moment with call termination and account lockdown or even just notification. These kind of features, data integrity, real-time, data processing, is exactly where we plugged in the blockchain or the distributed ledgers in our system. Now, I'm pretty curious, all of you are quite curious about the blockchain. Let's start with a quote. Blockchain is a perfect tool to provide information, transparency, immutability, and smart contracts, and to enable new business models. We strongly believe that our company, as a small telco, and then later on as a platform provider, can gain trust and can gain benefits from transparency. Although in our world it's not easy to have transparency as we handle data, and the data is not about ourselves, it's also about our customers, about our suppliers, then the blockchain is the perfect tool to provide us transparency without data disclosure. What is a blockchain? Essentially, it's a distributed database. You have a list of records. They are stored inside blocks. A block is a collection of records. Each block has a timestamp, and each block is connected to the previous block. This makes the data not modifiable. You can't update the data. You can just append. The blockchain has been invented for cryptocurrencies, although I'm really sorry, we are not talking about cryptocurrencies today. It's a tool that has been used to build Bitcoin, Ethereum, but the technology behind it is pretty simple to explain and totally unrelated to cryptocurrencies. When do you need a blockchain? You need a blockchain if you need a distributed database, condition one. You have shared write access, so multiple entities need to write into it. But you don't trust the other writers, or you don't even know the other writers. So the system should provide you consensus and endorsement to allow the modification of the database. What is the difference between public and private blockchains? Yes, because we have public and private blockchains. How many of you know the difference between a public and a private blockchain? Okay, let's try to summarize very quickly. They are both peer-to-peer, so you have multiple nodes working together. Every single node has a full copy of the blockchain, so it's a distributed database. Each of the peers have a copy. It's always kept up to date through consensus, so the peers are collaborating to keep the state of the database coherent, and you have immutability. So once something is written to a blockchain, you can't change it anymore. But what are the differences between a public and a private blockchain? A public blockchain, like Bitcoin or Ethereum, is a blockchain which is open on the internet, open to everybody. Virtually everybody can join a public blockchain. In a private blockchain, you have a different method to join the network. You need permission, either by the participants or by an authority or by a consortium. Private blockchains are designed to be high performance. This is one of the biggest issues with public blockchains. They're quite slow. You can have 7, 10 transactions per second worldwide. With private blockchains, you have different channels. So you can build, with the same network of peers, several channels with very high throughput. You can have high level transactions per second. And the most important one, the third one, private blockchains support ACL. So you define in the smart contracts who can read, who can write, and which fields of a given transaction can be read and wrote by the participants of the chain. What is Hyperledger? Hyperledger is an effort, an industry-free effort hosted by the Linux Foundation to put together different implementations of private permission blockchain in the open source ecosystem. There are more than 100 members. There you can find a few of the very famous names like IBM, who is investing a lot. In particular, today, we are going to talk about Hyperledger Fabric, which is a specific framework inside the Hyperledger ecosystem, which has been donated by IBM and Digital Asset to build blockchain-enabled applications. It's like a framework you can build your application on. Let's see an example. Okay, this is concrete. We can try it. We can give it a try. Let's say that we want to write a chain code, which is the Hyperledger Fabric name for a smart contract. It's a piece of source code can handle transactions to write CDRs in the Hyperledger. So we are a carrier or we are an operator. We want to write our CDR inside a specific channel to share it with our business partners. We have an entity, generic entity called participant, and we have several fields we want to store in our CDR. So let's start from the assumption that we already have a Hyperledger Fabric node running in our infrastructure. How does it work? Well, it's pretty simple. Here you have a model file. A model file is the definition of the basic entities you have inside the blockchain. So here you have a CDR. It's pretty simple. This is a sample code again. You define the fields, call ID, caller, callee, date times. You define the account, which is a participant, and the transaction. It's a call. You define the basic entities you will manage inside the blockchain. They are like tables in an SQL database. You use model files to define assets, participants, transactions, events, and other kind of models you will use when combining transactions. As I've told you, you can use access control, so you can define who can read, who can write. Again, this is a simple implementation. We say that CDR can be read by the subscriber, so the one who is paying, actually, but the operator, the one who is handling the call, can read and create the CDR. Using ACL, you can build channels, you can build different permissions based on your business goals to let just part of your data available to some of the peers. Query file, pretty simple, just like SQL. You can query the blockchain. It's a database, so you can get information out of it. And obviously, the information goes through the ACL, so you have the security managed by the infrastructure. So blockchain is about being decentralized and distributed. And we believe this is a very, very important point because you have no man in the middle. You have no central authority. You are taking part to a network of peers that are sharing a set of data and give the possibility to be completely transparent with their business partners. And we strongly believe that transparency is the key to build trust. You can think about fabric nodes in a very similar way of the mail servers. So these are enablers. You have one fabric node in your infrastructure, and you have access to potentially unlimited applications you can build on it. It's just like a mail server allows you to send emails to the world. Blockchain is about moving value, not just information. We describe the CDR. This is the low-hanging fruit. We can think about this small example as the basis for intra-carrier settlements and reverse charges. But you have potential complex applications you can build on blockchain, like peer-to-peer routing using enum, or handling the number portability, or the transfer between operators, or provisioning devices, or carrier-to-carrier or subscriber-to-carrier payments based on token. So this is the message I want to leave you at the end of the presentation. Are you ready to join a consortium of telco operators? Are you ready to join a blockchain with some of your business peers? We believe this is the future. We believe in a couple of years, it will be common to have a fabric or equivalent node inside your infrastructure, and to start sharing data with your business peers. And especially if you are like us, a small company, we are not a countrywide operator. This is an enabler to provide our business peers better service. Read about it, think about it, document yourself, because it's just a matter of implementation, and it will be the future. So thank you very much.
Thank you. Thank you. So, 40 slides in 30 minutes. I'm impressed by the Italians. I thought only Lorenzo can do so fast speaking. Was good volume of speaking, but impressive number of slides. Thank you, Fabio. And question here, question there.
Yes.
Hi.
Excellent. Hi. Excellent idea. How about deleting? Because, I mean, obviously with CDRs, you have an obligation that you have a retention period. And with a blockchain, it's not too easy to delete stuff anymore. But normally you would need to automatically delete CDRs after a period of time, because you cannot keep them forever, right? So is this possible already?
Yes, it is possible. In particular, it depends on the implementation, but in particular, Hyperledger Fabric allows you to build different channels. And different channels are like different blockchains. So don't think about the blockchain as one big entity. It's just as one possible database you can build inside an infrastructure. It's quite common, for example, to have one Fabric node to join several channels, so several blockchains with totally different, unrelated entities. So you have a blockchain with your business partners providing you traffic, and you have a different channel, so different blockchain for IoT or messages or another kind of business. So it's possible to build blockchains that are time-based, for example, that are time-bound. This is one of the possible approaches, but really it depends on the implementation. In this talk, we tried to explain you the big picture, but it really depends on the technology you are going to use. Blockchain is a generic technology that has different implementations.
Okay, one more here, and maybe the last one after we have the break, and you can approach Fabio, the Evosip guys, because we need to do also a bit of giveaways of gifts.
Okay. Thank you for the presentation. My question is about concurrency. So if we have a lot of calls in the same time, and as you show on your distributed system of nodes running in the Kubernetes, how the concurrent records will be done in the CDR database if you have blockchain. So one record is inserted, all the nodes have to sync, and only then the next one, or how it's?
Again, it depends on the implementation. For Fabric Hyperledger, it's a bit different, because you have special nodes in the network called orderers that are doing exactly that job. So they are getting transactions, they're building a block, and what you are writing into the blockchain, in fact, is not a single record, but is a block. And the block is part of the chain. So you have special nodes inside the system distributed among the peers that are building consensus of what a block is, essentially. This is how it works with the Hyperledger fabric, but there are different implementations. What is sure is that you can get quite high performances. It really depends on your traffic, although writing to the blockchain can be asynchronous. We are not talking about being synchronous. This is one of the things, for example, we do asynchronously. We don't update the blockchain each time we have a call start or a call end. It's just like building the CDR. You can do it later if you have to cope with the spike of traffic.
Okay, thank
Okay,
you.
thank you.
More details in the break. So I'm gonna extract. I'm the one that gonna decide the winners. But I have Alex presenting what the winner gets. So whoever field that survive from Evosip, it's